Hello everyone, we are at the 8th video of this spectral reduction tutorial and we have finally arrived to the wavelength calibration. In this calibration, we assign to each pixel in our spectrum a wavelength value. To do this, it is necessary that, during the night's observation, we record the emission from an arc lamp. This is simply the light of a hot gas, whose spectrum, as you know, consists in a flat continuum with strong emission lines. During the wavelength calibration, we take the arc lamp impression on the CCD, whose properties are known to us, and we export them to the astronomical object's FITS file. In IRAF, this procedure can be accomplished by the application of 4 tasks: identify, re-identify, fit coords, and transform. The application of this task is rather straightforward, especially the last 3. However, for the first one, you need to prepare a few files in advance. Let's get into it. First, we need to make a list with the lines from the arc lamp. To that, we need to download the arc lamps from our telescope website. In my case, I have here the one from the William Herschel telescope. In these documents, we have plots of the arc spectra for all the given grating configurations. The important thing is to find the one which covers your wavelength range and which includes all the gases. For example, I am using a copper, neon and argon lamp with a 300 grating. So I need to use this one, 300 grating with copper, neon and argon. Very good. At this point, we need to open our spreadsheet program. Myself, I use the one of LibreOffice. And now we need to write these emission lines into our spreadsheet. This must be done in a single column. Here I have mine. Okay. I know this may seem a bit tedious, but let me give you a few guidelines to make this work worthwhile. First, it does not matter if you have emission lines beyond the wavelength range in your FITS files. This means you can use the same file for any configuration of the telescope as long as it uses this arc lamp, and of course it has some emission lines in the given wavelength range. Second, it is very important that you generate this list from original plots for a given lamp. Let me explain. In a manual such as this one, you will find a list of all theoretical lines which can be generated by these gases. For example, this one over here. You might be tempted to copy this list directly into your spreadsheet. Nevertheless, you should not do that. Many of these lines are very weak, or worse, they might not be in your CCD recording. However, if IRAF reads all these lines, the quality of the matching can decrease when two values compete for the same emission line. So again, try to make this list from actual plots. And third and final advice, following the previous reasoning, you must check with the telescope supervisors if the lamp produces additional lines. Let me explain. In some cases, there might be contamination in the lamp with non-expected gases. It can produce emission lines even stronger than the intended ones. You can still use them, but you need to know their exact location. That means their wavelength. Very well, that's all I wanted to tell you about the emission line list. Once you have it, you must save this file as a comma-separated value. Very good. You can close it. And by the way, if you were wondering which PDF viewer I am using, it's called Ocular. It is very handy because you can change the orientation of the pages by going to View, Orientation, and Rotate. Moreover, you can also use it to grab sections of a PDF file and convert them into image files. Okay, let's close this one as well. Now you need to prepare what I call a legend with the emission line values of your ARC FITS files. Myself, I do that with Impress. This is the PowerPoint of LibreOffice. Here I have my file. In here, I have simply pasted some screenshots of my arc lamps open with IRAF. Once I compare these plots with the graphs from the maps of the William Herschel telescope, I have written over the lines the corresponding wavelengths. You might be asking, why do you need this? Well, as you will see in a few minutes during the wavelength calibration with IRAF, we need to select emission lines at the beginning and at the end of the plots. If you have a great deal of arc lamps, it is really efficient to prepare in advance figures with the lines already tagged. And also at the same thumb you will be working with. Okay, we are ready to go. You can open IRAF, and since this is the first time we use this task, we're going to change its default values. As always, confirm with your literature the configuration needed for your objects. You can access all the tasks we're going to use for the wavelength calibration within the long slit package. Very nice. And now, EPAR identify. Here we need to change a few values. The first one is match. We're going to increase the coordinate list matching limit to 10. In the feature width, we're also going to increase that to 7. The threshold feature for centering, we increase that to 10. And the number of iterations, we're going to activate that, but only one iteration. That should be all. And now let's run this command. Here, the first tag is the name of our feeds file with the recording from the arc lamp. The second one states that our files are vertically aligned. And finally, chord refers to our CSV file with the emission lines in this lamp. Okay, let's run it. And I shall make this window bigger. Very nice. Now, we need to zoom over the edges of this plot to tag the lines. We can do that with W and then E and E. Once again, W, E, E. Okay. Now we take a look at the plot we prepared before, and we can start tagging a few lines. To do that, we press M over the line we know, and we type its value. This one, for example, is 4,879.86, and this one over here should be 4,965.04. Great. And this one over here, 5,456. Very nice. Now to go back to the original zoom, WA, and the same over the other edge. WE, E. Okay, and I know that the last one is 7,723.8. Enter. 7,635.1. M 6,717.02. Okay, and we'll go back to the whole plot. We only need to tag a few lines, but it's important they are well spread. Especially, they must be located at the edges of the spectrum. At this point, we need to press L key as in load to import the lines from our text file. L. There you have it. Actually, I think there is a limitation on the maximum number of lines which can be imported, but with 20 or 30 it should be more than enough. You should notice as well how the overall shape of the spectrum has remained constant. That's a good sign. You should be wary of big deformation. Now we press F to fit. As you can see here, we have a fitted line with 53 points. And as in other ISP windows, we can press D to delete those who deviate a lot, like this one. Nice. This one as well. This one as well. In any case, you should remember that there should be points all over the wavelength range, especially at both edges. So I'm not going to delete those. I fit again. Very nice. The residual is below 0.05. And now we should take a look at the line's IRAF hashtag. We leave this window with Q. And now we can use the plus and minus keys to move along the lines. Let's zoom a bit first. W, E, E. And now with the plus sign and with the minus, we move around. And in the left bottom corner, you can see the wavelength value. Okay. WA. WE. If you see that a line has been tagged but it's not actually there, or like in this case there are 3 lines very close which compete for the same value, you can delete them with D. Okay, we move again, and finally, okay, acceptable. By the way, if you have problems with the fitting, you just need to delete all the lines and you can start again. But in our case, we're happy with the results, so Q. And now remember to say yes to write feature data to the database. At this point, the identify task has created a folder within the arc fits file location. Here we have it. This file has the calibration data for this lamp. If you ever have problems with the identify task, for example, if you have the spectrum collapsing into one point every time you fit, it doesn't matter what you do, you need to delete this file, for it could be corrupted. However, that's not our case, so let's go into the second step, which consists in using re-identify. This task takes the information from the previous one and produces a map of the dispersion distortion in the dimension of our file, in our case, rows and columns. But before using it, let's change some of its default values so it matches the previous one. Here we have it. And yeah, we can override previous solutions with each use. Trace reference image, no. We can increase also the maximum number of features which may be lost, 5. The threshold, we increase it again to 10. Match to 10 again. And verbose, yes, we want to see the output. That should be all. And now we can run this command, in which the first and second tags are the arc lamp file. The other parameters, yes, we have already visited them. So let's run it. As you can see, This task is calibrating each of the columns in our ARC file. In the final column, we have the RMS, which is very close to the one we got in the identify task. That's good. Now we can run feed coords. This task is used to transfer a set of user coordinates into an image. For example, in this case, we want to fit the wavelength range we just measured into our ARC file. Moreover, since we already use re-identify, this fitting will include both columns and rows in our feeds frames. The application of this task requires several steps, but let's consider them on the go. According to the guide we are using, the one of Phil Massey et al. For long-sleeve spectra, the default configuration of this task is good enough for us. So we just need to run this command, which only has the name of the arclamp feeds file. Enter. And now, in this window, we have a plot of the residuals along the rows of my ARC files. The global value of the residual is 0.05, which is fairly good. Overall, it is important that these residuals are evenly distributed. In this task, each array of values can be accessed with a keyboard key. For example, X for the original input image column positions, Y for the input image line positions, Z for the user input coordinates, and S for the fitted user coordinates. Finally, if you want to plot the residuals, you can use the bar. Why is this important, and how can you use it? Well, try to press this key combination: X, S, Y, R, R. Okay, what have I done here? By pressing X followed by S, we assign the fitted coordinates to the horizontal axis, and then by pressing Y key followed by the S key, we assign the residuals to the vertical axis. Finally, by pressing R again, we redraw this plot. In here, we have the same plot as before, but this time with the fitted user coordinates, which in this case are the wavelength values from our ARC calibration. It is interesting to take a look at the input positions alignment. You can do that by this key combination: XX, YY, R. By pressing twice the X key, we assign the input image column position to the horizontal axis, and twice the Y to assign the input image line position to the vertical axis. And again, we press R to redraw. If you have, like myself, vertically aligned frames, you can do the opposite. You can use XY, YX, R. In both these plots, and the point of using them is to confirm that you have a linear fitting. All these points should be aligned to confirm the quality of the application of your re-identify and identify tasks. If there are some points which are not aligned, you can use the D key. For example, over here, D. And now you are given the option to delete a single point or a constant in the X, Y, and Z coordinates. For example, if we press X, we delete this line. Once you're happy with the fitting, you press Q, and again, remember to go back to the IRAF terminal and say yes to right coordinate map to the database. Yes. Very nice. We are almost over. We just need to run the transform task, also located in the long sleeve package. Let's take a look at it. And here we just need to change one feature. Good. Conserve flags per pixel? No. What does this parameter mean? Once we import the user coordinates into our scientific object, we will just interpolate the pixel intensity from the previous images. No more operations. That should be all. To save. And let's run this command. The first flag is the input scientific object name, while the second is the name of the output file. The third one corresponds to the arc lamp frame, which is now perfectly calibrated. And the flags parameter, you already know it. Let's run it. Very good. As a result, this task gives us the starting and ending coordinates in both axes, as well as the number of pixels. In any case, the best way to confirm the quality of the wavelength calibration is to actually take a look at the images. In my case, however, since I'm analyzing H2 galaxies with a non-zero redshift, I need to use an additional command to take into account the redshift. In this command, we use the Doppler correction task, in which the only parameters are the input and output names and the redshift of the given object. Let's run it. It's done. And now let's open our spectrum with DS9. Let me move this. Okay. As you can see, there is a new set of coordinates with the wavelength. And let's take a look at H alpha. And as you can see, it is very close to its value of 6563. So the wavelength calibration has been successful. Great. Okay, this is all I wanted to show you in this video. In the next one, will be dedicated to just one task, a PAL. Thank you very much for watching and see you soon.